Okay, so we're going to finish up the lesson that we started in class today, looking at our seventh test, which is the second test in section 11-4, which is the limit comparison test. And in a lot of ways, this is similar to the comparison test that we looked at earlier in this lesson. Okay, so the limit comparison test says to suppose that a sub n and b sub n are series with positive terms, okay, where a sub n and b sub n are both greater than or equal to 0. Okay, so what the limit comparison test states is that if the limit as n goes to infinity of a sub n divided by b sub n is equal to some number c, where c is a finite number and c is greater than 0, then either both series converge or both series diverge. Okay, and if you look at the note down below, the note says it doesn't matter what series is a sub n and what series is b sub n. Okay, so a sub n can either be the series that we are given in the problem or the series that we are comparing to the given series, and the same thing for b sub n. That can either be the series in the problem or the series that we are comparing. Okay, so I'm going to work out the two examples that I do for the limit comparison test either way. Okay, so I'll do one of them where I'll make the given series be a sub n and the series that I compare it to b sub n, and then the other one I'll make the series that we are given b sub n and the series that we are comparing it to a sub n. Okay, and the limit comparison test is going to work in both ways. So when we utilize the limit comparison test, just like we did with the comparison test, we're going to be given formulas that or series that represent or look similar to a geometric series or a p-series, but are not geometric series or p-series. Okay, so we have to compare the series that we are given typically to a geometric series or to a p-series. Okay, so when we look at our examples, the directions ask us to test the series for convergence or divergence. For number 1, we are given the sum from n is equal to 1 to infinity of 1 divided by 3 raised to the n power minus n. Okay, so for this one, I'm going to go ahead and let the given series be my formula b sub n. And then what I want to do to choose a sub n is, like, I want to think about, when I look at that series formula, what would the end behavior of that series formula be? And when I look at my denominator, like, the term that's going to have the largest impact on the end behavior is going to be the exponential term. Okay, so what I'm going to compare b sub n to is I'm going to compare it to a sub n, which I'm going to rewrite that as 1 over 3 raised to the n power. Now, I'm going to leave a sub n in that form, but we can also think of a sub n if it's 1 over 3 raised to the n power. That is also equivalent to 1/3 raised to the n power. And we know that that is going to be a convergent series by the geometric series test. Okay, so let's go ahead and take the limit as n goes to infinity of a sub n divided by b sub n. Okay, so that's going to be the limit as n goes to infinity of a sub n, which is 1 over 3 raised to the n power, divided by b sub n. So I'll just go ahead and write this step out here, but then I'm going to erase it in a second. So that's going to be 1 over 3 to the n power minus n. So if I'm dividing two fractions, I can divide by taking the reciprocal of the second fraction and then multiplying those two quantities. Okay, so when I take the reciprocal of the second fraction, that's going to become 3 to the n power minus n over 1, and then we're going to multiply those two fractions together. Okay, so when we do that, we get the limit as n goes to infinity of 3 raised to the n power minus n over 3 raised to the n power. And then what I'm going to do here is I'm going to take that fraction and separate it into the difference of two fractions by taking each term in the numerator and writing it over the denominator of 3 raised to the n power. So 3 to the n power divided by 3 to the n power is going to be 1 minus n over 3 raised to the n power. And then what I can do here is I can take the limit as n goes to infinity of 1 minus the limit as n goes to infinity of n over 3 raised to the n power. And when I look at the second limit, so the second limit here, as n gets large, both the numerator and denominator go to infinity, so we can use L'Hopital's rule for that. So the limit as n goes to infinity of 1 is just 1, minus, I'm using L'Hopital's rule for the next limit. Okay, so that's going to become the limit as n goes to infinity of the derivative of the numerator, which is 1, divided by the derivative of the denominator, which is 3 to the n power times the natural log of 3. And as n gets big, that denominator gets large, and 1 divided by a huge number goes to 0. So this becomes 1 minus 0, which makes that limit finite and also makes that limit greater than 0. Okay, so we can utilize the limit comparison test. So I'm going to write up like my justification for the limit comparison test here. Okay, so since the sum from n is equal to 1 to infinity of 1 over 3 raised to the n power converges by the geometric series test, which we're going to abbreviate as GST, then the given series, which is the sum from 1 to infinity of 1 over 3 to the n power minus n, also converges by, we're going to abbreviate the limit comparison test as LCT. Okay, so again, if the limit is finite and greater than 0, then that means that either both series converge or both series diverge. And since the sum from 1 to infinity of 1 over 3 raised to the n power converges by the geometric series test, that forces the given series to converge by the limit comparison test. Okay, so I'm going to have you guys work through number 2. All right, and what I want you guys to do for number 2 is let's go ahead and work it through the other way. So let's make the given series here be a sub n. And what we're comparing it to be b sub n. Okay, so you have to figure out what you need to make b sub n, work through and calculate that limit, and then determine if both series converge or diverge. All right, so go ahead and pause the video to do that. And then you can go ahead and unpause and we'll work it through together. Okay, so again, the way I think about what I want to pick the series to compare the given series to is I want to think to myself, like, what would the end behavior of like the given series be? And the end behavior is going to be what the highest degree term is, okay, of both the numerator and denominator. So the highest degree term on top is going to be 2n squared. And then on bottom, the highest degree term is going to be the square root of n to the 5th power, which is n to the 5/2 power. And when I simplify that, that's going to become 2 over n to the 1/2 power. Now, just looking at this series here, so if our series, like the formula for b sub n, is 2 over n to the 1/2 power, like that series would diverge by the p-series test. Okay, so that's something that we can keep in mind as we work through this. So the b sub n is a divergent series because of the p-series test, and that is a p-series. Okay, so what we're going to do here is we're going to take the limit as n goes to infinity of a sub n, which is 2n squared plus 3n over the square root of 5 plus n to the 5th power. We're going to divide that by b sub n, which is 2 over n to the 1/2 power. And again, if I'm dividing two fractions, I'm going to take the reciprocal of the second fraction and multiply. So I'm just going to go ahead and rewrite that as times n to the 1/2 power divided by 2. Okay, so when we take the limit as n goes to infinity of this, we're going to get 2n to the 5/2 power plus 3n to the 1/2 power over 2 times the square root of 5 plus n to the 5th power, which, again, the way I like working through limits of this type is I like determining the end behavior of the numerator and of the denominator. So the highest degree term in the numerator is going to be 2n to the 5/2 power. The highest degree term on bottom is going to be 2 times the square root of n to the 5th power, which is 2n to the 5/2 power. And then that fraction simplifies to 1, thereby making that limit 1. Okay, so since, and now I'm going to go ahead and write up my justification. So since the sum from 1 to infinity of 2 divided by n to the 1/2 power diverges by the p-series test, which I'm going to abbreviate as PST, then the sum from 1 to infinity, so our given series, which is 2n squared plus 3n over the square root of 5 plus n to the 5th power, that also diverges by the limit comparison test. And in a lot of instances, guys, with series that you look at, if you can use the comparison test to test for convergence of or divergence of the series, the limit comparison test can also frequently be used as well. Okay, so you can use one or the other in a lot of instances working with series. Okay, so that's it, guys. That'll wrap up the lesson in 11-4. And hope you guys have a great rest of your day. Hope you guys have a great weekend. We'll see you all in class. Take care, everybody. Bye-bye.